For this example, we're looking at a situation here of a tug and a coal barge, which is cruising along with the engines on the tug turned off. They're moving to the left with some speed of V1. And at some time, then there's a winch here on the back, on the stern of the tug, that begins to pull in the cable that's connecting A and B in such a way that the velocity of the barge relative to the tug is this number here of VB with respect to A. What we want to find out is the speed of the tug while this is going on, and then also what's the average value of the tension in this cable over some period of time of delta T. So what we want to do first, I think, is look at A and B together. So if I look at A and B, we're asked to ignore water resistance. So as we look at the FBD of this is A, and then this is B. The only forces that we have are some weight forces and buoyancy forces like this. The point being is that there is no net force acting on the system of A and B together in the X direction. So for A and B together, the summation of forces in X is a 0. So this thing moves regardless of what's happening with that winch. The momentum of that system remains unchanged. So we have the mass of the tug, VA1, the mass of the barge, big M, VB1, is always going to be equal to M, VA2 plus big M, VB2. And it says at the beginning these two are moving with the same speed. So this becomes then just M plus M times this known initial speed here of VA1 is equal to MVA2 plus MVB2. So that is what's coming from our conservation of linear momentum for A and B together. And it's conserved because there's no net force acting on A and B together in the X direction. What we also know is that VB with respect to A, that's this known speed, which is the speed of B minus the speed of A. So from this, we can say that the speed of the barge then, VB2, is equal to VA2 plus this known relative speed. I can substitute this back into the momentum equation. I get M plus big M times the known initial speed VA1, and that's equal to then to M VA2 plus big M VA2 plus the known relative speed between A and B. So the right hand side of this becomes M plus M VA2 plus big M, the mass of the barge, times VB with respect to A. What we want to find out is VA2. So VA2 then is equal to the sum of the masses, the tug and the barge, times the initial speed of everything. Subtract away big M VB2 VB with respect to A, divide it by this, which is the total sum. So I can reduce this down to the fact that VA2 then is equal to VA1 minus the ratio of the mass of the barge to the total mass of the barge plus the tug times this known relative speed, which is dictated by the rate at which that winch is pulling in the cable. So from here it's quite clear that the tug is going to decrease in speed by an amount which is related to the mass of the barge to the ratio of the mass of the barge to the total mass of the barge and the tug. So that's what we get. Now the second thing that we're asked to find is during this occurrence, what's the tension force in the cable that connects A and B? Well, we couldn't get that from our original FBD. We purposely looked at A and B together so we didn't have to deal with that force. But now if we separate these out, we look at A and B by themselves, then we have in X direction, we have a tension force equal and opposite of A and B as that. So now we're in a position where we can find something out about that tension force by looking at, let's say, A by itself. When we sum forces in X, we have a tension force T. So then, since we're looking at A by itself, the integration of that resultant force in time is equal to the mass of the tug by itself times the change in speed. So again, since we isolated out A by itself, we're looking just at the force on A, and we're looking at just the mass of A. So this becomes the integration of the tension force in time. And by definition, if you integrate this force in time, that's exactly equal to the time over which it occurs times the average value of that force. So the average value of the tension force in the cable T is going to be the change in momentum for just the tug divided by the time over which that occurs. So I think the important thing about this problem is the FBD that you draw depends on what you want to find out. In the first case, when we just wanted to find the change in speed of the tug, we made the tension force internal. We didn't want to deal with it. So by doing A and B together, there's no net force in X, and we were able to find out what the speed of the tug was after we began to winch in that barge. But for the second part, we actually had to find that tension force. Then we looked at A by itself. You could have equivalently looked at B by itself. The point being is you cut the two apart, you expose that tension force, and then you can now find out information about that on the average here and what that average tension force is during the time the winch is bringing in the barge.